Hi, I'm Bob. Welcome back to 5 Minute Econometrics, a program designed for elementary econometric learners looking for a general understanding of the basic econometric concepts and estimation methods. We have learned 6 classical linear model assumptions in previous topics. The sixth assumption among them is known as the normality assumption or the normal distribution assumption. We will have a close look at this assumption today. The normality assumption is about the distribution of the error term in the linear regression model. For a linear regression model, if the population error term epsilon is independent of the explanatory variables and is normally distributed with a mean of 0 and a constant variance of sigma squared, then the model satisfies the normality assumption. The normality assumption does not play a role in demonstrating that the OLS estimators are unbiased estimators or the best linear unbiased estimators. We know that the first 4 classical linear model assumptions lead to unbiased OLS estimators, and the first 5 classical assumptions result in blue, that is, the OLS estimators have the smallest variance among all linear unbiased estimators. The normality assumption is the 6th classical linear model assumption. On the one hand, it is required to obtain the exact sampling distribution of T and F statistics so that we can carry out hypothesis tests. In other words, the normality assumption is for constructing the test statistics and carrying out statistical inference after the regression. On the other hand, it does imply a stronger efficiency property of the OLS. The OLS estimators have the smallest variance among all unbiased estimators, not only among the linear ones. Since we assume that the error term epsilon is normally distributed, we can show that the outcome variable y is also normally distributed. Under the normality assumption and the random sampling assumption, the error terms are independent, identically normally distributed random variables. An important property about independent normal random variables is that a linear combination of independent, identically distributed normal random variables has a normal distribution. Therefore, the outcome variable y is also normally distributed. The expected value and the variance of y can be calculated as follows. This is why the distribution of the outcome variable looks like this in the graph. Similarly, normality of the error term translates into normal sampling distributions of the OLS estimators. We can prove that the OLS estimator beta hat is also normally distributed. Beta hat can be expressed as a linear function of the error term. We can also obtain its expected value and variance. normally distributed OLS estimators are the starting point to construct t-statistics. When we standardized a normal random variable by subtracting off its mean and dividing by its standard deviation, we end up with a standard normal random variable. To test hypotheses about any single parameter in a population regression model, we need t-statistics. It differs from the standard normal distribution in the fact that we replace the error variance, sigma squared, with its estimate, sigma square hat, which can be calculated from the sum of residuals. Thus, the standard deviation of the beta hat is replaced by its standard error in the t-statistics. When we write a regression model, we try to satisfy the normality assumption by making the outcome variable y closer to the normal distribution. One method is to use the logarithm of the variable. For example, when we use workers' wages as the outcome variable, we usually take the log. After using the transformation, the distribution looks closer to a normal distribution than the level term of wages. If we have a large sample, we can drop the normality assumption because the OLS estimators are asymptotically normally distributed in a large sample size. This is called the asymptotic normality of OLS. The normality assumption is not needed for asymptotic analysis. We can still use the OLS method and make value inferences even when our data violates the normality assumption, as long as our sample is sufficiently large and other classical linear model assumptions are met. Today, we have discussed the normality assumption for classical linear regression models. We can take the logarithm of the outcome variable and use large samples so that the statistical inference and hypothesis tests are more accurate. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.